today's presentation is on soft contact lens material. I don't know, it would need one video or two video. Let's move and we will try to discuss some really important concepts and then we'll move forward. Okay, and contact lens material. So let's move forward. So what is contact lens? A corpuscle or glass or plastic that is applied directly over the globe or cornea to correct refractive error or to change the cosmetic looks or to protect the disease or the injury of the cornea. Yes, it means basically optical use, therapeutic use, injury, and cosmetic use basically. So that's three uses, isn't it, for contact lens? So optical use to correct refractive error, therapeutic use to basically protect disease or corneal injury, and cosmetic use. Yes, we know. So two type of soft contact lens, contact lens materials are soft contact lens and rigid contact lens. So basically rigid gas permeable, isn't it? So rigid contact lens means PMMA, so no gas permeable. So we are going to talk about soft contact lens. So basically that. So history, just one slide. We know Leonardo da Vinci basically illustrated the concept of contact lens, and in 1952, Otto, which produces the first cross-linking gel that is still used. That is HEMA, yeah, hydroxy, ethyl methacrylate, polyhema or PHEMA, and it was transparent and absorb around 38% of water content. Yes, around 40%, 38% of water content, and exhibit good mechanical property. And that's the first contact lens material is a soft contact lens material. Yes, so soft contact lens material, the first word soft contact lens material is HEMA. Yes, so let's come to the soft contact lenses made by polymers, basically hydrogels. Hydrogels are made from the water solon. What do you mean by water solon? Material that is swelled when you contact with the water. And cross-linked, definitely cross-links means links with the hydrophilic polymers, which are flexible and compiled. So a lot of the soft contact lens material is made base of the HEMA. HEMA is basic substance, and we add another component which basically increases hydrophilicity, isn't it? That's the concept. Yes. So what are the properties of material that we really wanted to know? Because see, in contact lens world of contact lens, it's really important that under which basis you select which material for a particular patient. So for example, if someone is marginally dry, then which material you select. If someone is perfectly okay and someone travels a lot, like someone fly 5 days he is in US and 5 days he will be in uh, Dubai or anything else. So what are the professions and what are the conditions, what are the environmental conditions, what are the ocular conditions, and including everything, how you are going to select the certain contact lens, because we don't have universal contact lens, do we? Some contact lens has some disadvantage, some has another advantage, disadvantage. So we have to select from the plethora of contact lens material, isn't it? So we must have a knowledge as an optometrist that soft contact lens materials property, so that you will select good contact lens for your patients, isn't it? Good contact lens material. So that's why property of material is central important whenever you are at the clinic and with the patient, and actually try to figure it out which material will be better for the patient. Okay, so let's discuss. So property of the material. Yes, optically it should be transparent. We will talk about it. Mechanically it should be some strength, isn't it? Yeah. Surface property, which is crucial. Water content, oxygen permeability, we have already talked about oxygen permeability in separate video. It's like, yes, large video. Fluid and ionic ion permeability is very important and very less care topic in case of property of material. Refractive index, definitely, and Soul factor and dimensional stability. We will going to cover everything, and we are going to cover nomenclature and another points too. So let's move further. Okay, what is optical transparency? We want our contact lens material optically transparent, isn't it? Yes. Our contact lens material need to be transparent in order to achieve maximum visual performance, or it transmits over 90% of light of the visual part of the spectrum. Basically, every contact lens, we want every contact lens to be transparent more than 90%. So this is the very first problem when, as a scientist, many of the scientists try to incorporate hydrogel material plus silicon. Okay, so they lose transparency. That's the very problem. Where that's If you read the history of silicon hydrogel, that's one of the great problem, that when people try to incorporate silicon and hydrogel, because hydrogel is hydrophilic and silicon is hydrophobic, and when they try to mix it, the transparency loss. And without the transparency, what's the use of contact lens, isn't it? Okay, so that's one point. So mechanical property means the main important mechanical property is physical strength, durability, impact, isn't it? So that's a mechanical property. So it's significantly can affect the more contact lens is harder, less comfort, isn't it? Visual performance is depend upon the mechanical property. If you blink the contact lens and contact lens wipe up very sharply, then definitely there is a problem. And fitting behavior is directly differed by the mechanical property. Physiological impact, yes. Durability is also depend. The more harder the contact lens, chances are more durable, yes. In hydrated state, most hydrogel are soft and flexible, definitely. That's why we call it soft lens, isn't it? uh, Besides from marketing, yes. So hydrogel states the most hydrogel lens are soft lens, and because it's soft and flexible. In dehydrated state, hydrogel lens become hard and brittle. So when you just experiment with the soft contact lens, you put the soft daily disposable contact lens, if you are trying to just throw it out in dustbin, then put it there some place and see in the next morning. So it's really hard when it becomes dehydrated. So dehydrated state, obviously hydrogen lens lose the water and it will become hard and brittle. So definitely in hydrated state it will be soft. Yeah, isn't it? That's the swelling. From dehydrated state you put in the water and it will swell. That's swelling factor, isn't it? Yes. So mechanical property. So several factors affect the mechanical property of the hydrogel material, such as material composition factor. Another is very important, polymer processing factor. It means if there is a lot of, what do you call that, cross linkings or not. Yes, in general, equilibrium water content (EWC) of the hydrogel lenses and its modulus is decreases. So basically means whenever you increase the water content, so basically modulus of elasticity, modulus gets decreased. It's always like that. Yes, whenever you increase the water content, modulus of elasticity decrease. Whenever you increase the water content, at the same time refractive index decreases. It's always like that. Yes. So now we come to the very important property. Besides oxygen permeability, I think surface property is another elephant of the room. So it directly affects its interaction with tear film and consequently its biocompatibility with ocular environment. What do you mean by that? Surface property means, see, remember, if you put contact lens, and what happened with the front surface of the contact lens is it directly interacts with the upper lid conjunctiva, isn't it? Upper lid palpebral conjunctiva. So it frequently contact, whenever you blink, the upper lid palpebral conjunctiva will rub the front surface of the contact lens, isn't it? Yes. So then what happens if front surface of the contact lens is surface property is not good? Then there will be problem. There will not be biocompatibility of the ocular environment, and there will be problem like simple common problem is uh, what do you call that, papillary reaction in upper palpebral conjunctiva. Yes. So what do you call it? Weightability. It's very important, very important. We are going to discuss about weightability. Weightability is describe the tendency of liquid to spread on the solid surface. Basically means if there is a contact lens surface, then if you put, let's take example of water here, this yellow water, then that water spreads over that surface. Yes, that's the concept. So in vivo weightability means in actually eye, the ability of the tear film is spread and maintain itself over the contact surface. So surface property, weightability in relation to contact lens has traditionally been assessed with in vitro using the contact angles, isn't it? It's not basically doing in eye, in vitro, in a laboratory. So basically analyzing the contact angle analysis. So we are doing these things with the contact angle analysis, and I think you have heard the techniques, isn't it? The captive bubble technique, sessile drop technique, and so on. When a drop of liquid is placed on the solid surface, the angle is formed at the solid liquid air interface. That angle is called contact angle, and whenever that angle is lower, basically means it uh, basically surface is more wettable. Whenever angle is higher, surface is less what do you call it? Surface is less wettable, isn't it? Yeah. So surface property, the contact angle can be advancing and receding. I will definitely talk about what is advancing and what is receding. Just don't panic. So advancing angle is an angle formed when the liquid is advanced over unwetted surface. Basically means liquid is spreading in unwetted surface. At the same time, receding means receding contact angle is angle formed when the liquid is withdrawn from the surface. If liquid is withdrawn from the surface, it's called receding surface. If liquid is advancing and moving forward, okay, so that's called advancing contact angle. So there is two types of contact angles. Okay, so the difference between these is called hysteresis. Okay, so that's another point. Let's move. So what is the advancing and what is receding angle? Okay, see, when liquid move forward on the unwetted surface, basically surface is unwetted and liquid is moving forward to make it wet, it's called advancing angle. And at the same time, when liquid is retreated from the wetted surface, basically means withdrawn from the wetted surface, then it's called receding angle. Yes, so basically surface condition is dry, unwetted, then we put a drop and then it moves. Surface is wetted previously and we withdraw the drop, that's called receding angle. So represented, so ease of initial weighting, basically what's advancing angle actually represent is how easily it will be weighting. And at the same time, what receding angle creates idea is how easy liquid withdrawn. Okay, so ease of liquid withdrawal. So typical values is usually advancing angle is larger than receding angle. I think it's exactly opposite in captive bubble technique. Maybe we will see in upcoming slides. So usefulness is to show the material resist initial weighting. It's very useful for that purpose. Okay, and receding angle is used to show how strongly liquid stick to the surface. That's use of receding angle. So basically means these are the things. Okay, so that's what we I have talked about, that the smaller the contact angle, the better the liquid is spread over the surface. We want basically our surface has a smaller contact angle and the surface is more wettable. That's what we want, isn't it? That's the angle made by this picture where it shows the angle made by a liquid. Yes, so as far as I can discuss is there are three main techniques which is used for surface weightability. Okay, that's his sessile drop method, another is captive bubble method, and this is Wimsley plate method. So there are three techniques. Okay, so sessile drop method is basically how it works. Its principle is a small water drop is placed on the surface of in air, and the drop profile is imaged and the contact angle is calculated from the tangent. So basically that's picture. This picture is a picture actually sessile drop method pictures, and what it measures the static and dynamic, basically advancing and receding contact angle. Okay, so what the pros of this method is simply widely available and standard textbooks, and these are the things. But what's the con is for soft hydrogel results may be distorted. So that's the thing. So suitability for the contact lens material is okay for the lens material if measured on the flat test coupons. Okay, that's the thing. But what is captive bubble? So don't you think the name itself called captive bubble? Bubble is captivated somewhere. The sample is immersed in the liquid and air bubble is held against it from the below and imaged. The contact angle is measured at the solid liquid interface. So I think for these techniques you should go to ICL module. So in icon module, you will see a good pictures and you will have that idea. Okay. So at the same time, what it measures static and dynamic contact angles underwater. Underwater, just remember, and advancing and receding by bubble size. So basically, it directly measures the wettability in hydrated state and very relevant for the hydrogel and actual lens conditions. So what are other things? Wimsley plate technique. What is that? Basically, a plate or strip of the material is dipped from the upward and withdrawn. Basically, whenever dipping, it's advancing angle, and whenever removing, it's receding angle. So that's the thing. So dynamic contact angle, advancing and receding from the force of meaning. So force based, not optical, and is standard in the surface science text can be stresses and surface tension. So I think I have made some point here, and I'm not going to discuss a lot about this technique, and I'm not going to take a lot of time here. But yes, that's what you have to understand, that there are three techniques and these are the very famous techniques. There are other techniques too, but I don't think we have to go there and discuss about things. Okay, so let's move forward. So water content. What is water content? It's very important, and I'm going to talk about water content very deeply. So equivalent water content of a hydrogen lens is defined as, basically how it defined, the in equation, upper part is weight of the hydrogen water in a polymer, and lower part is total weight of the hydrated polymer into 100%, okay, into 100. So equivalent water content of a hydrogel may vary depending upon the environment conditions. So see, what do you mean by, it's mean by pH, it's mean by tonicity, it's mean by temperature, it's mean by humidity, and there are a lot of things. But remember, so if, what if we made the weight of the water like 100%? Is it possible? It's not possible at all, because you if you made water 100%, it means the total weight of the hydrogen polymer is also 100%. Yes. So is there any place for the actual hydrogel material, that hema? No. So that's why it's always a range. We cannot move to 100%, and it's for sure we cannot make it for 100%. And another point I want to make is, see, water itself has decay of around 80. So is it possible that hydrogel contact lens, we move water content like 75 up to nearly 80, not exactly 80, but so it's impossible that hydrogel contact lens has the property of decay because of water. So if we have 100% water, it's decay approximately 80, so we cannot make hydrogel contact lens up to decay of 80. Okay, it's very important, you have to know this concept that water has decay of 80. It's very important. Okay, so oxygen permeability, I think I have done good job in that video. Just go to the decay by T video and understand the concept. Okay, so oxygen permeability, as I've already showed, 10 to the power minus 11, you should know it's decay, because and centimeter square, the unit is very important. 10 to the power minus 9, you know, decay by T, transmissibility. Okay, so that's, this is graph, it's very useful graph. See, equivalent water content, whenever water content increases, this is the line for soft contact hydrogen contact lens. So decay increases, yes, because in hydrogen contact lens, the main component that bring oxygen move from anterior surface to posterior surface is water. More the water, higher the decay, simple. But in case of silicon hydrogel, higher the water, see, higher the water, if you increase the water, decay decreases. Yes, because in silicon hydrogen material, the main component that passes oxygen is not water, it's silicon itself, the actually bond of silicon, oxygen, silicon. So that's why you have to understand this concept, that in hydrogel contact lens, the more water is, the more decay. Right? In silicon hydrogen, yes, not always, but yes, in first generation, second generation, it is there that more the water you have in silicon hydrogel, the less the decay. Okay. So oxygen permeability, I have already told about it a lot, so I'll skip it. So there is obviously Holdenberg's criteria, the very heat criteria. It's according to it daily wear 24, extended wear 87, and Harvard and Bonanno criteria was 1999. For so basically avoid anoxia throughout the cornea. Okay, so in Holdenberg's criteria, it's avoid the corneal edema. In Harvard and Bonanno criteria, they avoid anoxia throughout the entire cornea. That presupposition is different in both conditions. Okay, Holden's criteria and Harbin Bonanno criteria. Holden's criteria is 1984. Harbin Bonanno criteria is 1999. So in Harbin and Bonanno criteria is 35 decay for daily open eye condition and decavity 125 for close eye condition. So it's not about daily wear or extended wear. It's about open eye condition and close eye condition 10 to the power 9. Let's remember this point. And for open eye condition, we need to have decavity about 35, and for close eye condition we need to have decavity 125, so that there will be no anoxia throughout the entire cornea. So that's the concept. Okay, so we're moving forward. So what are the methods that is here for decay measurement? Yes, so there are famous method too is polarigraphic method, it's fat method, and coulometric method. So that's two famous method. Yes, definitely gas to gas or manometric method is another method. So I'm not going to discuss in detail about it, but I'm going to roughly discuss about it. So polarigraphic method, what it does is lens planes over the cloud type and polarigraphic oxygen sensor and 32, and oxygen diffuse throughout the lens and current of proportion of oxygen is flux. Then lens move between wet and the dry reference and condition is calculated. That's how it does. Okay, just pause the video and you can see things. Okay, measurement quantity decay oxygen permeability directly can get decavity if you divide by the thickness. Coulometric uh, coulometric method is a sealed chamber with the different O2 partial pressure on each side of the lens, and O2 diffuse through the detect and through is detected by the colorimetric sensor. That's what it does. So it measures the steady state flux. Here it's important decay oxygen probability without oxygen consumption by the sensor. So that's what. And this I think you read by yourself. Pause the video and read another advantage and disadvantage type of use too. Okay. So let's move to fluid and ionic permeability. What do you mean by that? So development of silicon hydrogel material has highlighted the importance of the so-called hydroluric permeability and water transport, because see, whenever if there is no passage of fluid or ionic ion from the contact lens from anterior to posterior, so contact lens get stuck. So that's the problem. So minimum level of hydraulic permeability is necessary in order to maintain the adequate movement. That's what I'm talking about. If there is no permeability of water and no permeability of ions in the contact lens, so contact lens get stuck, so it will not move. That's the main central thing you have to understand. It allows post lens tear film to reform between blinks, and thus reducing the elastic lens form binding to the cornea. That's why the concept. If you don't have that permeability of for ion and fluid in contact lens, there is a high chance that contact lens get stuck. It will bind to the cornea. Okay, so that's the concept. A refractive index, as I have already told you, ideally hydrogel fabricated for contact lens materials should have refractive index similar to the cornea, but ideally, but yes, not. So variation of refractive index in with equivalent water content in the conventional hydrogel in the most linear with the mostly hydrogel refractive indicates that within the this see 1.46 to 1.48 at 20% water content. Refractive index decreases as the water content increases. That's very important equation you have to understand. As water content increases, refractive index decreases. Finished. Okay, this remember this, and just remember gross idea about the refractive index of soft contact lens. It will be helpful in your journey. Fine, let's move forward. Swelling factor and dimensional permeability, I have already talked about it. Let's once again talk. So dimensional stability of hydrogel length refers to the ability to maintain original dimension under various conditions. It's very important. Yes, so it's depend upon any factors that will change the water content or the swelling behavior of the hydrogel. So we have already talked about the content of water, it's like pH, humidity, and all these things. Factors that influence the swelling factor may include temperature, pH, and tonicity. Yes, swelling factor and dimension permeability. The swelling behavior of particular important during manufacturing of the contact lens. I have already told you, whenever you manufacture the contact lens, soft contact lens, it's in the dry state. Yes, and then you put that contact lens into the solution and let it swell, isn't it? So especially in lath condition, during the lathing process, a smaller steeper contact lens, the greater power is made, so that when it hydrated it swells and requires dimension, and the power is, we can get that power and dimensions. Yes, we have to know the swelling factor first, so it will be clear when you understand the manufacturing process. Okay, so I think I should stop here, because from here I think I will going to talk about in next class, because it's too much. It's 26 minutes. So from here I'll talk in next video. Okay, so I think this done. Choose.